Hello, everyone. Welcome to our session. Today, we're going to talk about telematics analysis in Spark. First, let us introduce ourselves. My name is Zhang. I manage the driving safety data science team at Uber.
I'm Neil Parker. I'm on the driving safety engineering team as a back-end engineer.
The driving safety team is probably the largest producer and consumer of telematics data at Uber. But lots of this work are actually in collaboration with our maps and the sensing and perception team. They've built some really cool services that we consume in the pipeline. Here's today's agenda. I'll kick off by giving an introduction to telematics. I'll talk about what is telematics, the types of data used for telematics analysis, some common methods for processing telematics data, as well as some applications of telematics to driving safety. In the second part, Neil is going to talk about the ends pipeline for telematics solutions. So, what is telematics? In the broad sense, telematics is the service that uses telecommunications to transmit information collected from sensors in smart things, such as vehicles or some smart buildings. So it falls into the general field of Internet of Things. Our primary focus here is on vehicle telematics, which concerns using sensor data from vehicles to understand how, when, and where the vehicle operates on the road. To do that, one solution is to install the sensors onto the vehicle. However, in general, that's not a very scalable solution. The increasing use of smartphones for navigation has created a new and a scalable way to collect telematics data. Smartphones have lots of built-in sensors, and they offer very efficient ways of wireless data transfer. When the phone is fixed to the vehicle, the sensor data collected from the phones can be used to understand the vehicle movements. So there are several advantages of using smartphone-based vehicle telematics over solutions based on vehicle sensors. Smartphones are widely available. They are relatively cheap, and they have short upgrade cycles. However, the drawback is that the sensors from the phones typically have lower quality compared to sensors installed to vehicles. In addition, the sensors from the phones measure the motion of the phone. We cannot assume that the phone is fixed with respect to the vehicle, which complicates the interpretation of data collected from sensors that are orientation dependent. We will have some examples later on. The rest of this talk is going to be focused on smartphone-based vehicle telematics. So the core pipeline for telematics analytics consists of the following major components. First, we need a system that allows us to collect sensor data reliably, with high quality, with high frequency to support the analysis. Second, most of the raw sensor data are very noisy. We need to apply signal processing and statistical learning methods to denoise the data. After the appropriate pre-processing and transformation, we can make inference of vehicle movements, identify events such as acceleration, braking, turn, swerving, and the long stop, etc. Now, using a history of vehicle movement events of the driver, we can make inference of the driving behavior and the driving styles. There are two types of sensor data commonly used for telematics analysis. First is GPS, which provides the absolute location and the velocity of the phone. It is typically collected at a very low frequency, less than 1 data point per second. The second is IMU, inertial movement unit, which measures the relative motion of the phone. It typically has an accelerometer unit, which measures the three-dimensional linear acceleration of the phone, and sometimes a gyroscope unit, which measures the three-dimensional angular velocity of the phone. It is collected at a much higher frequency, oftentimes more than 20 points per second. To give you some idea what the data look like, This plotter here shows some sample readings from GPS speed and the 3-axis of IMU accelerometer and the 3-axis of IMU gyroscope. We can see that the IMU data are collected at a much higher frequency. They also seem much more noisy. We need to apply some signal processing method before working with them. So the information provided by GPS is often with a certain accuracy, depending on factors like satellite geometry, signal blockage, etc. Each GPS reading has a horizontal accuracy, which implies that the true unknown location is somewhere within the circle formed by the given location, and the horizontal accuracy as the radius. Because of this, the raw GPS typically do not fall onto the underlying road segment. For example, here, the black dots here correspond to the raw GPS traces. In order to address this, we apply a map matching, which is a commonly used method to snap the raw GPS to the underlying road segment. Map matched GPS locations are expected to be much more accurate in terms of both the locations and the driving directions. The second type of pre-processing relates to how the phone is orientated with respect to the vehicle. This is critical for using IMU data because IMU readings depend on how the phone is orientated relative to the vehicle. A slight change of the phone orientation will lead to very different IMU readings. Here is an illustration of that problem. Suppose we just rotate the phone in 2 angles around the z-axis. One is 45 degrees, the other is 90 degrees. The 2 resulting plots here look very different compared to 0 rotation, even when the vehicle has not moved yet. So before using IMU data, we need to estimate the phone to vehicle orientation and then align the IMU measurements to the vehicle frame. And then we use the aligned IMU measurements to make inference of a vehicle movement. So after pre-processing and transformation, we can derive driving events of interest. One such event is long stop while driving. The left plot here shows the GPS speed for a trip, where we observe the GPS speed is almost zero for extended period of time. Such long stop could be an indication of something anomalous happen. For example, the car has a mechanical issue or the car gets into a crash. However, it is not uncommon for normal trips to have long stops. So how do we distinguish them? One way to do that is to leverage maps data, for example, places of interest or road geometry, around the long stop to provide more context of the nature of the stop. To illustrate that, this middle plot shows 2 long stops from 2 normal trips. One is at a 7-Eleven, where the driver stopped to just go to the convenience store. The other is at a gas station, where the driver stopped to add gas. Compare these 2 stops with the last one on the right, where the car stopped on a highway over 1.5 hours. So this last long stop is more likely to be because of car mechanical issues or car accidents. We can also make an inference of vehicle movement events, such as acceleration, braking, speeding, and so on. It is very well known that drivers who frequently engage hard acceleration, hard braking, or speeding have a higher chance to get into accident or engage in dangerous driving situations. So these types of features are very good input to understand dangerous driving behaviors or identify dangerous driving situations. So here's another application. So using phone while driving can significantly increase the visual and manual distraction. Telematics data allow us to detect whether the phone is being handled or the phone is mounted to the windshield. So when a phone is detected to be not mounted consistently, we can send an alert to the driver or provide discounted phone mounts to the driver to incentivize the driver to mount their phones in order to help reduce distracted driving situations. So now I'll hand it off to Neil to talk about the Edge pipeline.
Hey, everyone. Yeah, I'll talk a bit about our Edge pipeline. So I'll talk a bit about the Edge pipeline. The rough agenda is we'll talk about the pipeline, past, present, and problems with solutions. But a quick thing before we jump in is just understanding how big our data is. So Uber does millions of trips per day. We collect terabytes of sensor data per day. And over a year, that's petabytes. So it's a lot of data. And we have other critical things as well, like in some cases, we need to quickly be able to calculate certain inferences if we want to build like products in the real world. So there's a lot of requirements here, which require some cool engineering. So I'm going to talk about past a bit. So when we started off doing things in the space, we started off with streaming because we started to build directly for products. We're using Kafka for I/O and Apache Samza for doing the actual logic, which is a streaming framework. And this was nice. It was in real time, except there were some problems. Namely, in our case, at some point, we want to look at data from 5 months ago over like a 3-month span. And this doesn't really scale to that. It's hard to use a streaming framework to batch process data, especially at our scale. So this is going into the present. I'm sure this is looks like a very complex diagram here. But if you guys notice what happened, our I/O turned into Hive tables, and our logic turned into a Spark job. And this is nice. We're using this for batch processing, and it's very flexible. So it sort of solves the previous problem where, hey, we have months of data that we want to just process all at once. This can do that. And now, I just have to show this. This is the actuality. So since we did migrate, and there are some cases where we still want things to be real time, we aren't using Spark streaming. Maybe there's another presentation you can go to today to learn about that. But our solution was we just split out the business logic, it's JVM code, and then we can reuse that for both streaming and for batch. And you might hear this referred to as a Lambda pipeline. But I won't talk too much on this. I'll jump again back to the present. And the present is complex. Sometimes we have more than one input. But this is actually really easy to do in Spark. We can write join logic in Spark SQL. In the streaming world, it can get a bit tough because you're dealing with state, you're dealing with time windows. It's generally easier to do this type of thing in Spark. And it's, made all ours easy. And just to show you guys how much more complex it can get, sometimes we output to multiple tables, I know. And another layer of complexity. Generally for batch pipelines, there are cases where we actually just want to run these every 24 hours. Like our use case isn't, we have to be super real time. We're OK with 24 hours. And Spark works really well with this in batch mode. We can just schedule it, run every 24 hours. And let's say it fails, we can just restart it. I mean, it's pretty flexible. That's what we like about it. So stepping back, and here's sort of how a pipeline works. I don't know if you guys saw that, so let me flip back and forth. We had one Spark job, input, output, and now we just kind of chain them together. And that's sort of the modular simplicity of using Spark here. And I'll show this. I know it's blurred. It's on purpose. This is our actual pipeline, just to show that things can get pretty complex, even if you have these simple modular things, especially when you keep connecting them here and there and everywhere. So it's a fun challenge. But now we'll jump into some concrete problems that I thought were kind of interesting, and hopefully you guys can learn something from them. First, I'll talk about data sources. So I talked before about joining this data together and then processing it. That works great if all your input is coming from Hive tables, which have a schema. Then you can join them in Spark SQL, right? It doesn't work so great if one of your inputs, for example, is thrift binaries. as it turns out, there's some teams at Uber that have some legacy data, and the data is really important to us. But it happens to be in this thrift binary format, which isn't immediately usable. So there is a solution. There's a link here. Basically, you can use a library. I'll have a PR out soon for this to fix a few things around. But these guys wrote some really great code. And basically, you can convert these thrift binaries to actual Spark SQL schemas and get that data into a Hive table. So now, we're just going to jump under the hood a bit of that, because I think this is an interesting aside, especially for those engineers out there in the crowd. Under the hood, basically, you're converting these Java thrift class instances to Spark SQL rows. But if you're like me and you think writing tests is hard, and generally speaking, writing tests for this type of thing can be a little difficult, what you do is you add that second arrow, which requires some effort. But then you can set up this encode, decode invariant. So you can generate random data from, well, I was using the Scala check library. You can generate random data and just pipe it back and forth and make sure that the one transforms back to the other. So this is a nice, easy way to write a test and be pretty confident that your code's working. And yeah, this is just tying it all back in. So now, again, it's very modular here. We have the job. We convert the thrift binaries to a Hive table. And now we can finally use it as input to our job. OK, this is a different problem. And my solution is fairly easy here. There's a lot of different things you can do to fix out-of-memory errors. I won't dive into them all. I'll jump into this specific solution because it kind of causes another problem. But one way you can fix a lot of out-of-memory related issues, at least the ones we were seeing, is you can increase the partitions that your job is using. So in our case, a lot of things were in SQL, and things were sort of breaking there. So there's this config spark.sql shuffle partitions. 200 is the default. If you make it something bigger, you might be happy. Maybe 2001, that's a magic number in Spark. And yeah, of course, you can play with other configurations as well. But I sort of cause you guys another problem. It's that if you increase your number of partitions, you go to write the table, you get a ton of files on HDFS. Unless you're coalescing beforehand, but then you might get an out of memory again. So we came to a different solution here. After our job runs, we just merge the Parquet files on HDFS. And this can be accomplished. There's Parquet tools. There's actually a jar you can download. You can do a Hadoop jar command, run the merge function, and concatenate your files together. Right now, we have some bash script to do this over a directory. If people are interested in that, I can try to get it through the open source stuff at Uber and get it out. But it's just some pretty simple bash code. And that's it for problems and solutions. I just want to take a second to say that we're trying to look towards the future with our engineering problems here and really understand what we can do with the power of Spark. So this is a graph we made. And so this is the fraction of hard braking events, basically different magnitudes of them. You can see that plotted here. And this is a map, of course, of San Francisco, just showing where sort of people are braking more or less, harsh or less harsh is what I mean. And this is really cool. We could even think about at some point, maybe we can share this with city planners and make the cities themselves better. Because we have pretty unique access to this ton of data at Uber. And it opens some really cool doors. And so, yeah, we just wanted to say thank you, definitely for you guys listening and everyone at Uber who helped us. You can email us if you have questions, but we also have actually plenty of time to take some now.
Great.
If you guys did have questions, there's a microphone over there, or if you really want to, you can just shout them out. If you don't have questions, we can accept that as well. So the question is, are we going to keep relying on collecting this data through cell phones if the sensor data isn't as good as what like car sensors could give us? Yeah. So it's true. The quality of the data that we get from phones isn't as great as like some really expensive sensors, but we can collect this at scale, which is quite powerful. And in fact, like sensors in general aren't too bad, especially when a lot of people actually have like Apple devices, and the sensors in those phones are actually like pretty reliable, and also like they're well calibrated, and it's not too bad. We do run into some issues in markets like India, where some phones, they may lack a gyroscope or accelerometer. Those are harder problems, but hopefully they're problems that sort of solve themselves over time.
Got a question here. Do you have any particular technology to deal to time series data? I would assume that you guys are working with time series data a lot,
Yeah.
right?
Yes, most of this time series data, we collected the GPS and the MU over time, over the, the course of the trip. Yeah, in order to do that, we have lots of, apply lots of techniques to process time series data. And we also use deep neural networks like LSTM, things like that to derive features that feed into the downstream machine learning models. Yeah.
Thank you.
Okay, so the question is, for the visualizations we showed, did we build some custom APIs or did we use some libraries? Is that the question?
Yep, for the maps.
Yeah, for the maps, we actually built those. So the maps you saw earlier in the presentation, it depends which one. There's one like GIF that Wayne showed that was inside the mobile app itself. So like our mobile guys built that. For the one you saw at the very end, like this one, there's a data visualization team at Uber, and they helped us create this. They actually open source a lot of things. Like they're one of our biggest open source contributors at Uber, so it's possible that you could create something similar. We use like an internal version of their like library and like software that they serve, but a lot of the stuff that they do is open source. Yes? The data store that we use for spatial data? Yeah, it's true. It can be difficult. I mean, if we're just storing things in Hive tables, generally speaking, we're not really doing any great sharding there on like geo regions. We do store like a field that tells us which city things are in. And there are different teams at Uber that are trying to solve this problem and for like real-time products. And I know they're using like a mixture of Cassandra configured in certain ways or Elasticsearch. And I'm not the biggest expert there, unfortunately. We can take the question at the mic.
Hey. Yeah, actually I have a question about the data quality. As you mentioned that for the projection device, it's basically provide the probably most accurate results. And for the cell phone, I mean, even from our company, we tried the windshield for those like a device that can attach to the windshield, and also provided like actually really bad accuracy compared to the projection. So for the cell phone, also at the beginning you mentioned that it's a kind of questionable of the low qualities. I was wondering for this study, do you do some comparison like for this like a low performance data, but compared to a more accurate device? Do you see the variation there and how off the results is?
Yeah, that's definitely a challenge. So we've done lots of work to analyze, what's the data quality variation even across different phone devices, and there's lots of variation. One of the things we do actually, one of the things you can do is actually you can train data by different devices, or it's just to give you a concrete example, some phones don't even have a gyroscope. You can just build a classifier using accelerometer versus a classifier that consumes data from both accelerometer and a gyroscope. And also, yeah, we do have some data collected from sensors on the vehicle that we can benchmark against. There's tons of work that looks into that to figure out how do we improve the quality of the data collected from sensors. There's tons of work you can do there to make it better. Yeah.
Okay, thank you.
Hi, you talked a little bit about your map matching. Is that done, I'm assuming in what you referred to as like a shared component across both your streaming and batch systems? Could you talk like a little bit more about how you do that map matching, what you match against, and if there's any other like components involved in that are perhaps open source?
Yeah, I can speak a little bit on that. So this is something that, there's a maps team at Uber, and this is something that they own. And they did a recent tech talk, which you should really try to find on YouTube, which will go into more detail, but I can give some general ideas behind it. Basically, we use underlying like road segment data from some providers, and there's a hidden Markov model that runs to actually map things to segments. And as far as doing that in real time or batch, they have figured this out. The real-time one is just a service that runs across some boxes. I think the difficulty there is like you have to load all that segment data into memory. I think they're using some scheme to like shard boxes geospatially. So they don't have to store all the segment data for like the world in a single box. So there are definitely challenges there. And as far as running it in batch, I'm really not the biggest expert. I know they have a solution, but I don't know exactly what it is.
Okay, thanks.
Hi there. So just wondering, your inputs, they mostly go to the Hive tables. Could you share with us the reason behind that?
Yeah, I can talk quickly, and if Wayne has anything to add, I'll let him. Yeah, so one reason is when we transition from streaming to batch, sort of the infrastructure at Uber is pretty nice in the sense that all the Kafka topics we had a schema attached to them, and they were being ETL'd into Hive tables. So that's definitely one reason. And the second reason is like the intermediate results that we have and we're outputting the Hive tables, a lot of times it's really useful to just have them there to run analysis over. Like even like data science analysis, sure, but even for like engineering analysis to make sure like measuring recall and other statistics about the data that you produce to make sure it's valid. So we find it to be powerful and helpful.
Yeah. Yeah, one thing to add to that is really data science needs to use lots of historical data when building the models. So having that data available in Hive is one of the best ways to address that.
So it's not really for performance or scale, but it's for flexibility. Is that?
Yeah, I would say it's more towards flexibility than other things.
Right, thank you.
Yep.
Hi, just a curiosity. When you mentioned the drivers who have more hits, they might have more accident than the drivers who have less brakes. So is there any solid evidence to prove that?
Yeah, there's lots of public research and studies showing that result.
Okay.
Yeah, it's almost, yeah.
Okay, so
very widely accepted these days.
Then what's the business outcome of that? So if Uber detects a driver has more brakes and the Uber will send out alerts to this driver to tell him you need to be careful?
Sorry, what was the?
So I'm just curious, what is the business outcome if you have a sensor on in the car and you detect this driver is driving the car with many brakes, and is there any alert sending out right away to let this driver know you are driving the car in very not really careful?
Yeah, so the stuff we showed here actually already in the Uber app, basically, we provided this dashboard to monitor to like show the driving styles or the braking events. So one of the things it can do is actually to help train the drivers, to coach the drivers to improve the driving.
The outcome will be like if you know this driver has many brakes or this driver is not really a careful driver, the outcome outcome will be the driver might need to pay more insurance to be part of the Uber program? Or I'm just curious.
No, I don't think we have something like that.
Okay.
Yeah, that you have to check with the regulation, legal requirement or something.
Okay,
like that.
all right, okay, thank you.
Hey, quick question on the Parquet files. You said you are using the merge tools to merge if there are like too many partitions, right? So is there any optimization reasons for doing that?
Sorry, could you repeat the question one more time? I didn't hear the first part.
Sure. So you had a merge tool being used to merge different when there are too many partitions, right, for the Parquet files?
Yeah.
Was that because of the optimization reasons or like?
Yeah, so we found the Parquet merge tool to just work well for this type of thing. So basically combining the Parquet files together. And it's because we were having out-of-memory errors, and then we started to create a lot of files. There are some other ways to reach a similar result if you just select the data in Spark SQL and then you coalesce it, right? If you're familiar with this function. And even in coalescing, you can see sometimes things went out of memory. So we thought this was a more general solution. And as far as optimizations, right now the thing that we're doing is pretty naive. We're just straight iterating through files and the bash script I wrote, but perhaps you could parallelize it to group things and then merge them in parallel. There's probably smarter things you could do. We just didn't need it. So yeah.
All right, thanks.
Yep.
All right, thanks, Simon.
I think we have one.
I got one more question, yeah. So with the intermediate Hive outputs, do you guys have any data retention policies to control kind of how much data you collect, and how does GDPR fit into that?
Yeah, there's definitely data retention policies. We're in a bit of a strange world. I don't really want to speak too much because I don't know a lot. There's certain restrictions that we have dealing with insurance-related data that we need to keep some of this for certain periods. But you're right, there's the whole recent stuff with GDPR. And they're trying to, from what I understand for the solution, I'm not the expert there, but they've implemented it more as a base infra solution for our whole company. And I'm not entirely sure how that works. I know if you look up Hoodie, Hoodie, that's a format that they've been switching everyone over to at Uber. And the idea is that instead of being immutable files, those are mutable files, which you can then store on HDFS. Yep.
All right, cool. Thanks, everybody.
Yeah, thank you.